Hello, I'm Anna Mackay and today we're looking at indices and index laws. So indices, what is the answer to this? -1 to the power of 1. Well, that comes out to be -1. Now, apologies in advance, in this slide we're missing the first line a couple of times. What about -1 to the power of 2? So squared. So that's the equivalent of -1 times by -1, so 2 lots of that. What do we get? We get +1. So noticing that those negatives cancel out. What about -1 to the power of 3? What pattern's emerging here? We have 3 lots of that -1. So notice that the number will still be a 1. Will it be positive or negative? Negative, because there's 3 of them. Those 2 would cancel out and then you're left with 1 more. What about to the power of 4? 4 lots of -1 multiplied together gives us +1. So summarising that, that's what we get there. What pattern do you notice? You might think that, okay, if it's an odd number, we end up with the negative sign, and if it was an even number of negatives, it's positive. But did that just happen because this -1 was an odd number itself, that 1 is an odd number? What about with an even number? What about -2? That's an even number. Let's see what happens. So this to the power of 1 gives us -2. What about -2 squared? That is 2 lots of -2 multiplied together. So we get the number 4 and it's positive. Those 2 negatives have cancelled out. What about to the power of 3? So you might in your mind think 2 times 2 times 2 gives you the 8 component, and then will it be positive or negative? It will be negative because there are 3 negatives, and to the power of 4, 4 lots of that, and we get a +16. So what pattern have we got here? Summarising that there. We have, if it is a negative number, and that doesn't matter if that negative number is an odd or an even number, to an odd power, so odd numbers, 1, 3, 5, 7, etc., the answer will be negative. So that's not telling us what the numerical part of it will be, but the sign of it will be negative. Whereas if it's to an even power, 2, 4, 6, 8, we'd end up with a positive answer because there'd be an even number of negatives which are cancelling themselves out. What about this here? -5 to the power of 4. So is that positive or negative? That power of 4, well, that 4 is an even number. So we're expecting a positive answer perhaps? Well, no, it's negative. And the reason is, these are different. If it was the one on the right here, -5 to the power of 4, then we would get a positive number because it is 4 lots of -5. Whereas the one on the left is, hear the difference here, 5 to the power of 4, it's the negative of 5 to the power of 4, not -5 to the power of 4. So essentially what you're doing there is 4 lots of 5 and it's the negative of that. So you're putting the negative on at the end, which essentially means you've got 1 negative as opposed to here where you have 4, if that makes sense. So summarising our index laws here, if you have the same base and they're being multiplied, you add the powers. One little technique that I have, and it might sound lame, is how do you remember that? If it's a multiply, if you turn that multiply sign slightly on its side, it looks like an addition. And that might be how you remember that it's an add. The second law here is the divide. Well, you've got something sitting on something that you might think, well, that divide line is a bit like the subtract symbol. And so it's a subtract of the powers. Next, the multiply rule. So you may remember back when you first learned how to expand brackets, the distributive law, you're essentially distributing that power on the outside to everything on the inside, and when you do that you multiply. So that's that law. Same thing here, it's distributing that power of n, so you have to share it with everything, not just the b. You might think, well, it's the b's closest to the n, so it's just that one. No, that's very wrong. Everything needs it to the power of n. Same rule goes here. You're sharing that n in with everything inside the bracket. To the power of 0, that law, anything to the power of 0 is 1. You could have table to the power of 0 and you would get 1. Provided A is not what? There's one thing it can't be, and that's 0. To the power of a negative number, we've got, you essentially flip it. So you go 1 over A to that power. So notice that the n is still there, but the negative sign has gone because it's been reversed. The same goes for if you have it as the denominator in a fraction with a negative power, you can shift it to the top and then it becomes positive. And this one over here to the right, remember that anything when you can't see the power has the power of 1 there, so that's playing on that same idea of that rule there. Okay, let's do some examples. Here we go. Simplify using index laws. So the first one here, we have 3 to the power of 5 times by 3 to the power of 4, and the rule is you add the powers. So you have 3 to the power of 5 plus 4, which gives us 3 to the power of 9. That's that one. The next one here uses the divide, and so therefore we're using a subtract. So we have for B 5 to the power of 3 subtract 5. And 3 subtract 5 is negative 2. Now we tend to write these with positive indices as we can, and so the other rule that we've learnt now is that you can shift it to the bottom to be the denominator, and that's 1 on 25. Simplify as much as you can, and C, we have m to the power of 4 multiplied by 3. It's not 43, and that leaves us with 12. Next, writing as powers of 2. So you need to be able to recognise certain powers quite quickly. When I say powers, I mean 2, 4, 8, 16. So hopefully you recognise that 16 is a power of 2, and it's the fourth one. So you might think of it like this, if you need to, and then we have 2 to the power of 4, 4 lots of 2. So 1 on 16 must be the same as 1 on 2 to the power of 4 there, but the question did ask us to write as powers of 2. So to answer this, we need to make it 2 to the power of negative 4. Now it's base 2, as opposed to the base being on the denominator. 1 there. That's not anything to do with 2, is it? Well, anything to the power of 0 is 2, so if we have base 2 to the power of 0, that would equal 1. Next one, the 4, we can write that as a power of 2, so that's base 2 to the power of 2 multiplied by 2 to the power of n. And now the rule is, if we have the same base and they're being multiplied together, we can add the powers. 2 to the power of 2 plus n. And the last one here, the numerator is fine, that's in a power of 2. The denominator, hopefully you recognise 8 as 2 to the power of 3 because it's 2 times 2 times 2. And then because they're being the same base and they're being divided, we can subtract the powers. And that's our answer there. A little bit more complex. Writing in simplest form here. So we have the 4 outside of the brackets. We have to share that in with each thing, not just sharing it with the A that already has the power. So our answers for that are, if I have enough room, I might write it next to it here. You might like to think of it like this first, and then that simplifies out to be 81, and notice that it's positive because it's an even power, times by A to the power of 8, and we got that because we did 2 multiplied by 4. The last one here, we have to distribute that 3 to everything inside, not just that 3 to the thing that it's sitting closest to. So it's not just A to the power of 6 or 5, whatever you might try. You have to share it with everything. So we would get negative 2 to the power of 3. And you might be asking yourself, where does that negative go? Well, essentially the negative is just with one thing. So you choose which one it goes with. My suggestion is put it with the 2. But you need to write that in brackets because otherwise you'll have what we talked about on one of the previous slides, that the negative won't get taken into account properly. And we have a squared all cubed over b cubed. So notice how that power of 3 has been shared out with everything inside the bracket. Tidying this up, negative 2 to the power of 3. So I like to think of it, I do the number part first. I go 2 cubed, I get 8. And then I look at that negative and I go, okay, it's an odd power, so that means it is going to be negative. So I'm going to leave it as negative 8. The a is 2 multiplied by 3 to give us a to the power of 6 over b cubed. Technically, I should write that without the multiply in between. There's our answer. And this one here, writing without negative indices. So we're essentially going to flip. So what is positive? The b is positive, so that'll stay on top. And what is negative will shift position. So the a comes down to the bottom and becomes positive, and the c goes up to the top. Just to write that better though, in alphabetical order, and for the c we don't have to put that 1 on there. If you're not sure about this rule about it flipping, my maths teacher at school always made the suggestion of, when in doubt, use real numbers. So this rule of 2 to the power of, say, negative 2, I'm telling you that it's the same as 2 to the power of 1 over 2 to the power of 2, which is 1 on 4. What would that be as a decimal? 0.25. I ask you to type into your calculator 2 to the power of negative 2. Go on, do it. And see what you get. And I bet you get, I hope you get, 0.25. So that's a justification that using this index law, where you make it positive and it's 1 over that, hopefully justifies to you why that rule is what it is. And the last one here, if we're asked to write in non-fractional form, that we have to bring this up to the numerator, and to do that it becomes negative. So I would write 2 to the power of all of this, please put it in brackets and make it negative there, and then simplify that. So we're essentially timesing both things by -1. And then the technique that we write is descending powers of n technically, so we put the n first. And that's our final answer. Thank you. The next one in this series is scientific notation. Thank you.